Hi. Okay, everyone. So today we have Samuel Tan with us from our very own CS department in the neighborhood. Samuel works with Andrew Childs and Dan Gottesman, and his main interests are in quantum error correction and fault tolerance. And today he will be talking about effective distance of higher dimensional hypergraph products and weight-reduced quantum LDPC codes. So Samuel, all yours.
Yeah, thanks for the nice introduction. You guys can call me Sam too. And then since it's a pretty small room, feel free to ask any questions in the middle of the talk. Let's try to make it interactive as much as possible. Yeah, and this is joint work with Lev. We are both like second year grad students at Quicks. And then yeah, let's dive into this thing. So for this talk, I guess I'll start off by sort of giving an overview of the results that I want to cover today, and then giving some preliminaries before sort of discussing what the main results are, getting more into the weeds of the details for like the proof and everything. And then lastly, we end off with a conclusion and some future directions that we can also discuss towards the end of this thing. So I'll start off by sort of explaining what is weight reduction. So perhaps in the context of classical coding theory, you can understand it as a technique that transforms an error correcting code into another error correcting code with similar code parameters while reducing the degree of the checks and bits in the tanagraph. And then this often comes at the expense of adding extra bits and checks. So one possible example is if you sort of if you have some sort of tanagraph that looks like this with a check and then 4 bits. So you could say that this check has like weight 4. And then if you want to reduce the weight of this check, one possible option for you is to sort of come up with 2 checks that looks like this. And then if you want to sort of maintain the difference between the number of checks and bits, you could also add another bit at the top here so that n minus k is like 3 or something like that. If you get what I'm saying.
Maybe quickly remind what these boxes and circles mean.
Oh yeah, the squares would be the checks, and then the circle would be the bits.
Right. What that means? What exactly?
So like the checks would be checking whether the bits have errors on them. So this is in the form of like a classical error correcting code. You have some checks, and then they will check the bits, and then if the bits has an error, if there's odd parity in this case, the check will give you a syndrome, and then you will know that there's an error there. And then
just say that there is a parity check matrix for the code, and you draw a graph from that matrix, so that your boxes are the rows and their circles are the columns.
Yeah. I was gonna get to that a bit more in the preliminaries. I was just sort of giving them like a sort of a graphical picture of like what weight reduction might look like.
But when you change the left thing to the right, you remove this condition that the 4 guys satisfy a single parity, don't you?
Yeah, this is not necessarily equivalent. I'm just sort of giving a flavor of like how weight reduction might look like by sort of decomposing certain checks into more checks and then adding additional qubits, additional bits to sort of retain some of the properties. But just to give a flavor of what weight reduction might look like. So before I start off with the motivation for weight reduced quantum codes, I also sorry.
Question, why do one want to reduce the weight?
Yeah, this is exactly what I was gonna get to. So this is perfect. It's a good question. So like weight reduction is probably not a very important in the classical sense, because when you perform error correction in the classical sense, you probably just measure every single bit in your code, and then based on what you read out from each of those bits, you can pass it to the parity check matrix, and then you get the syndromes, and from there you can perform decoding and then correction. So in some sense, the weight which will come in the form of the Hamming weight of each rows inside the parity check matrix, it doesn't really matter, because maybe if it's sparser, you could maybe do some sort of linear algebra calculations a bit faster, but it doesn't actually matter in the physical sense.
But that is not completely true. It is a good idea to have low weight rows for the reason that you can then perform your decoding in a local fashion, what they call belief propagation. And so in fact, this is the understanding behind the LDPC codes. the LDPC specifically because you can decode them locally, and then the weight of the row really matters. So even on the physical side, it plays a big role in classical picture.
Yeah, I think that's accurate. Yeah, just saying that it's like more practically relevant in the quantum side because you know, when we actually sort of perform like syndrome measurements, we cannot measure every single quantum bit because it would cause the superposition to collapse. And because of this, you know, we have to strategically sort of measure each based on each row of the stabilizer check matrix. So the weight now matters. So and another point is that, you know, most quantum codes, including the LDPC ones, they do have like prohibitively large stabilizer weights. In some sense, those large constants matter a lot because they result in pretty expensive syndrome extraction circuits with large gate counts. And then, you know, I've talked to some experimentalists. They say that it's experimentally hard to realize checks that have weights larger than 6 at the moment. It's almost impossible for 6. People are looking at 5, 4 or below as much as possible.
So is that like a hardware restriction that we have, that long range, for more than 6, you need long range connectivity, and that is currently not realizable in the hardware? Is that like
It's not just long range connectivity. I think just having 6 consecutive like checks, even if it's nearest neighbor, is also pretty challenging.
it's
Yeah, like there's like some I'm not fully familiar with the device physics, but that's what I've heard. And then those long extraction times, because the extraction time scales with the depth of the circuit, of the syndrome extraction circuit, and then the depth of the syndrome extraction circuit scales with the weight of the stabilizer check. How many sort of quantum bits you are trying to sort of check. And then a longer time will also give opportunities for more errors to accumulate. So that's also another motivation. And then finally, without well-designed syndrome extraction protocols, the code becomes more susceptible to troublesome hook errors. So in that sense, when you have faults on the ancillar qubits of the syndrome extraction circuit, they can propagate to the data qubits. And then if you have a higher weight, even if it's constant, you actually spread to more bits too, if that makes sense. Here's another picture to sort of maybe explain what the hook error and what effective distance is. So in this case, we have a very naive example where we have 1 ancillar qubit, and then we have 5 qubits over here. And then there's 5 qubits. You can think of this as a stabilizer that's checking x1, x2, x3, x4, x5. And then what happens here is that when you have an error in the ancillar qubit, it propagates down this entangling gates. So it gives rise to x3, x4, x5 as errors. So you see how 1 error now becomes 3 errors when we measure the syndromes. And then when you sort of apply this notion of degeneracy by adding like the stabilizer generator back to the error itself, the effective error is actually x1, x2. So what we see is that 1 error in the ancillar causes 2 errors in the actual code itself. And then if on average you say that, you know, every error causes 2 errors in the code, you can say that the code distance has been effectively halved. So there's this notion of effective distance that comes with the order that we measure the generators, as well as for each generator itself, what is exactly the circuit that we're using to measure it. And then obviously we can sort of make this more fault tolerant by adding more ancillar qubits here, and then sort of not allowing one error to propagate to every single qubit. But those bring in additional overhead in terms of the ancillar qubits required. So these are a couple of reasons why weight reduction is of, you know, practical interest. So now I just want to briefly talk about the weight reduction techniques that we are interested in for today's talk. They are proposed by Hastings back in 2016, but there were some slight issues with his work, and then I think he made some corrections and introduced some additional techniques in the 2021 paper. It's a very interesting paper. Would highly recommend people to check it out. So in this paper, he discussed several like techniques that work for any CSS stabilizer codes. So you just put in the CSS stabilizer codes. There are some algorithmic ways to sort of, you know, output another CSS stabilizer code where the maximum weight of any stabilizer check is now reduced. And then the maximum number of checks that any qubit is involved in is also reduced. And then there is some overhead associated with this technique. Basically, the size of the code, the number of qubits will increase by a factor that's sort of proportionate to the weight of the checks of the initial code. So if you were LDPC initially, you can bring it down to like, like roughly weight 5, weight 4 for your X and Z stabilizer generators. But your overhead will be increased by like, like 5 cube or like 4 to the 3 or something like that, which is sorry, the original weight square or cube, which is pretty prohibitive for near-term standards. So this is pretty much an asymptotic result, but I think the techniques are pretty interesting, and then it's useful to sort of think about them to see if we can uncover better weight reduction techniques. And in addition, these weight reduction techniques are also interesting if you guys are interested in locally testable codes. One of his technique that we'll be discussing today has been used to construct and modify quantum locally testable codes. And then those have implications in Hamiltonian complexity if you're interested in those things. And then lastly, for today, at least for this work, these are kind of like the problem statements that anchor like the research direction that we were sort of looking at for this project. How fault tolerant are Hastings weight reduction techniques? Fault tolerant is a term that people like to throw around a lot, and then it's not really properly defined. So in this case, we're sort of interested in, let's say, a code before weight reduction, they have certain fault tolerance properties. Maybe they perform pretty well even when you have single ancillars used for your syndrome measurement circuits. After you perform weight reduction, are they still amenable to single ancillar measurement circuits? Whether they suffer like significant like distance loss or this kind of stuff. And then
quick question. So you said we reduce the weight and there's an overhead associated with that. What does increase overhead in what?
Overhead in the number of qubits in the resulting code will be quite a bit larger than
building a new code which is longer.
Yeah, a new code will be longer. There will be more stabilizers used, but the degree that means the connectivity is like a lot more sparse.
Slower. And what about the error correction?
The distance will be comparable, will be either the same or sometimes you can the technique I'll be talking about today will actually allow us to boost the distance of the code. Yeah.
But then how many logical qubits will that get new code encode?
So in the techniques that Hastings was interested in, the number of logical qubits remain the same.
So then your rate decreases.
Yeah, your rate decreases, but you gain more practical benefits in terms of the things I've discussed earlier. And then yeah, but the rate decreases by a constant factor. So it's
well, everything is constant. The rate is between 0 and 1.
Oh, I mean like the
rate means the number of logical qubits divided by the number of physical
yeah. But
but huh?
You mentioned they have some constant.
We'll see. But then in this,
oh, I could go back to that again. So it's yeah, that's a good question. It's basically this was an example of a single ancillar stabilizer.
That's why I asked.
Oh no,
Maybe everybody knows. I don't know.
no, it's a good question. I didn't place enough emphasis on that. The idea is that if you have like a error correcting code, a quantum error correcting code, and this is like the stabilizer matrix. These are like maybe n qubits here that these are the columns, and then the rows would be like n minus k, and then you can have maybe x here, which like you can think of them as you performing the stabilizer element generator xxx on the first 3 qubits, and then maybe you have z here or something like that, and so on. And then for each of these generators, we need to perform syndrome measurement, and then to do that we need some sort of circuit, which is the one on the left over here. And then this circuit, you can there are many ways to design it. Some are more efficient, some are more susceptible to errors. So in this case, we consider like single ancillar ones. They are like very cost efficient in the sense that we only require 1 ancillar qubit for reading out the errors. And then the way we sort of perform syndrome measurement is that we entangle like the qubits of interest. So in this case, if it's the first row, the 3x at the top, we will entangle this 1 ancillar qubit with 3 qubits that we are supposed to sort of check. And then if there are errors in those qubits, they will propagate up the entangling gate into the ancillar qubit. So if it's XXX, it anti-commutes with the Z errors. So if there are Z errors here, they will go up here, and then they will sort of affect your measurement result of the ancilla qubit. Yeah, so that's kind of how it works. And then you know, you could have multiple ancillas, and then you know, you could always sort of argue that multiple ancillas would be better, and then maybe you could sort of detect whether errors in the multiple ancillas are going into the code and stuff like that. So so we're interested in single ancilla because it's easier to analyze. And at the same time, if you can show that a code performs well with a single ancilla circuit, you know, it shows that you can sort of reduce overhead by sort of using something simpler to perform error correction. Yeah. Any other questions?
We know that a single ancilla circuit exists for a given code.
Well, it always exists in the sense that you can just you know, just use one ancilla per generator, and then you just literally just use this circuit. This is the most naive way to do it. The question is, you know, how good or bad the performance will be when you use a single ancilla one. And then today, one of the goals is to sort of, you know, convince you guys that for the higher dimensional hypergraph product codes, which is a really popular quantum error correcting code nowadays, at least like they have a lot of other nice properties. We want to say that you can use single ancilla, and we should be fine with that too. Yeah. Are there any other questions?
What do you mean by performance exactly? So like, I'm assuming that the code is fixed, and let's say you use a single ancilla versus multiple ancillas. What exactly changes?
So there's this notion of effective distance. That's one way we can sort of examine this thing. So as I was saying earlier, maybe I could just remove all this scribbles. So you can create more space. Yeah, the idea is that if you use a single ancilla, you just have one error here, right? In the ancilla qubit, this is like a bit flip error, you can think of it that way. It actually propagates down to 3 different quantum bits in our quantum error correcting code. So this is what we call a hook error because it looks like a hook. It goes down. And then because one error now causes 3 errors in our code. And then at the end of the day, we're only interested in the number of errors that cause in our code, right? But we know that it was created by just one error itself. So you know, and then there's some argument that we made over here that this error is actually only equivalent to 2 errors. So one error, one real world like error, we call it elementary fault, creates 2 errors on the code. You can think of it as like, you know, the code's effective distance has been halved because now you need half the number of errors to generate whatever, like, you know, the number of errors in the actual code itself. So when the distance is halved, then, you know, you get some sense of how many errors you can correct, and then that affects the error correction performance. Yeah. Yeah, those are good questions. Yeah. If we are good, we can proceed. Yeah, so you know, this is what we are interested in. And then this is like, I'm going to be covering 2 results from the paper today. This is like almost a pretty useless statement because it's so informal and doesn't cover anything. But just to give some idea of like, you know, just to sort of show that it addresses the problem statements. You know, given a CSS code that has effective distances dx and dz under some single ancilla syndrome extraction schedule, and like what, you know, you ask a good question, now like a schedule always exists, you know, for single ancilla, just how good or bad it does. So maybe this effective distance dx and dz is not excellent. But because it's also LDPC, it's only like a constant factor below what its original dx and dz is. And then we show that, you know, there exists some single ancilla schedule that the effective distances of the resulting code that has undergone Hastings reduction largely preserve. Again, largely preserve is also very ambiguous. But we show that for thickening and choosing heights, which is the technique that we'll be discussing today, it's effectively like completely preserved. Yeah, which is the nice, like you know, it shows that the weight reduction technique itself is, you know, sort of fault tolerant in that sense. Yeah. Then this result, which might be a bit more interesting for people who are, you know, into quantum LDPC codes, you know, we want to say that higher dimensional hypergraph product codes have no troublesome hook errors. And troublesome hook errors just means that, you know, your effective distance doesn't decrease at all due to those hook errors. And then when using any syndrome extraction circuit, which means that, when you use those codes for quantum computation, you have a lot more flexibility for like how you want to do those things. Yeah. And I also want to add two comments about this informal statement. There is actually a recent book by a couple of folks at Yale who showed that this is true for just regular hypergraph product code, which I will introduce later too. And then so this is kind of like generalizing the result too, as a form of like a corollary from the previous main result, that it now holds for higher dimensional ones too. So maybe it's not too surprising if you know of the original result itself, which I will briefly talk about too. And then lastly, I want to say that higher dimensional hypergraph product codes have a lot of very interesting properties. They are very efficient logical gates. Again, it's a result that came out earlier this year. They showed that you can do fast and parallelizable logical gates on higher dimensional hypergraph product codes. And then they are also amenable to single shot decoding. I'm not super familiar with like classical error correction literature, but I believe like single shot decoding is sort of thing there. So maybe you guys already know what it means. But the idea is that, you don't have to like perform that many rounds of extraction and decoding. Yeah. So let's just go through some preliminaries. Feel free to stop me at any point of time if it's unclear what they mean. So before we begin, we need to sort of briefly introduce the poly group. It's just tensor products of I, X, Y, and Z. So for those who are a bit more familiar with the classical literature, like X would just be the equivalent of bit flip, 0 to 1. And then Z is plus to minus. This is something that's more like to minus. It's just in a different basis, that's all. And then there's an overall phase of plus minus 1 or plus minus I. And then the stabilizer code, you can sort of let S be a subgroup that's abelian of the poly group with negative I not in S. And then if Q is a quantum error correcting code with code space corresponding to S by this, let it be the whole like a set of quantum states such that any element in the stabilizer group M stabilizes the quantum state. That means it leaves it invariant. Then we say that this is a stabilizer code. Yeah. Is there any question at this point? This should be more familiar to those with previous exposure, but I'm happy to explain a bit more about this if that's it. Yeah. Okay, if that's good, then I want to talk a bit about CSS code because CSS codes are the one that Hastings Techniques work on. So this is pretty much the code that we'll be working with. This is just basic definitions. I'm not going to explain too much about it. It's just saying that there's a representation that we can use for like the poly group after we sort of mod out the phases. So after you mod out the phases, you can write it something like this. For the identity, you can have 0 on the left, 0 on the right. For the poly X, you have 1 on the left, 0 on the right. Y, you have 1 on the left, 1 on the right. Z, you have 1 on the right and 0 on the left. So if you have something that looks like, X, Z, X, with, in this particular order, you will have something that looks like 1, 0, 1, and then 0, 1, 0, something like that. So this would represent, this, representation itself would capture like what this poly operator XZX is. So it's just a representation. And then, well, this representation isn't actually very important in the stuff, but it's just useful to sort of understand that for CSS codes, it's just like, a subfamily of stabilizer codes where as long as you can choose your stabilizer generators such that, you can write them in this particular form, where this is the binary symplectic representation. So what this means is that the top rows, you can gather all the Z stabilizer generators, and then the bottom row, you can gather all the X ones, such that each row itself only consists of Z, and each row either consists only of Z or X, which means that all your generators will be, each generator itself will be solely Z's or X. And then this is a pretty nice property because you can sort of analyze the error correcting error correcting performance of the code with respects to bit flip errors and phase flip errors separately. So it sort of brings us a bit closer to the classical picture in that sense. Yeah. And then to sort of talk a bit about the other techniques that will sort of be brought in the discussion later, we have to talk a bit about homology and chain complexes. So a chain complex is basically a sequence of finite dimensional vector spaces. So each of these vector spaces will be capital A with some index at the bottom. And then each of those vector spaces are sort of equipped with a boundary operator that maps it from aj to j minus 1. And then a co-boundary operator that maps it from j minus 1 to j. And then these boundary operators, you can think of them as group homomorphisms because each of those vector spaces are groups themselves. And then there's an additional requirement, partial j plus 1 has to be equal to 0. And there's a similar sort of condition for the co-boundary. Yeah.
What's the boundary operator?
The boundary operator is like you can think of it as a matrix if you want. And then in each of those aj and aj minus 1, they are vector spaces. So you could have vectors in those vector spaces, and then this matrix brings you from one of those, a vector from aj vector space to aj minus 1 vector space. And then I'll give you like an intuition shortly. Yeah, like a more like a, and then I just want to state the definition first. And then this condition, what it's saying is that if you have some, if you have some like a j plus 1 dimensional object, after you apply the first boundary thing, you get a j dimensional boundary of it. And then in a j dimensional boundary, when you apply the boundary operator again, there's no more, like it's just like trivial because the boundary of a boundary is trivial in this case. It's just the way it's defined. And then I can sort of draw something very quickly to sort of give you an idea of what this thing would look like. And then, yeah, I was just saying each of those vector spaces, it's F2, and then the dimension of the vector space is given by n sub j. And then in each of those vectors, you can think of them as j-dimensional objects that we call j cells. And then each vector itself is a j chain. So like it's just a way of sort of yeah, and then the set of j chains form a group. And then a more geometric kind of intuition is that 0 chains, you can think of them as vertices because vertices are 0-dimensional. 1 chains are sets of edges because edges are 1-dimensional, and then 2 chains are sets of plaquettes. Yeah. Yeah, so let's say if I draw like a square at the bottom of Q, and then you can think of this as this is a 2-dimensional object, and then this is a 1-dimensional object. Those are blue lines. And then the points that I don't know how to get another color, but these points are the 0-dimensional objects. So this could represent some sort of error correcting code too, or some sort of chain complex in this case at least. And then when we say like we ask what is the boundary of this thing? Let's say I have a one chain. A one chain is a vector of 1 cells. So like let's say those darkened blues thing is a 1 chain because they are it's a chain of edges, right? And then when we look at the boundary of this thing, you see that the boundary of this particular edge that I'm hovering over is this thing, right? Those two 0-dimensional objects. And then the boundary of this thing, it's this thing and this thing. The boundary of this thing is this thing, this thing, and then the boundary of this thing is this and this. So because it's Z2 and then every edge boundary sort of overlaps once kind of thing. So there's actually this cycle itself has no boundary in that sense. Yeah, does that make sense? Yeah. Okay, I can give another example later, but this is just an idea of like how you could sort of represent like the chain complex, like geometrically, and then you just associate each things with some sort of dimension, and then you can look at the boundary of each entity inside the thing.
So the NJ has nothing to do with GL, except that the index.
Yeah, it's just an index that sort of associates the N to the jth dimensional vector space.
So in that NJ dimensional vector space, you have a J dimensional object. Sorry.
Could you repeat your question, sir?
So in that NJ dimensional space, which is the AJ, you have a J dimensional object.
Yeah, this J dimensional is just like you can just think of it as like a geometrical dimension, like you know, some sort of maybe J dimensional hypercube kind of thing. If we sort of go back to this picture, and within that itself, it has because it's F2NJ, right? So there's 2 to the N to the J different entities, 2 to the NJ J dimensional hypercubes in this vector space.
So you simply code, let's say, vertices with NJ dimensional vector, and those vertices you assemble objects of various dimensions.
Oh,
Does this make sense? Yeah. So and then just some additional definitions. An N cycle is an N chain Zn that satisfies, like, you know, it has no boundary pretty much. Because the boundary of this is like the boundary operator, right? The boundary of this N chain is trivial. So and then the set of N cycles form a group Zn. So N here is the same as the J as previously. It's just a different notation here because J was just used there, but N is a bit more common. And then N boundary is an N chain Bn, where there exists some N plus 1 chain An plus 1 such that so what it's saying is that an N boundary is the boundary of some N plus 1 chain. That's all. Okay. So to make it more explicit, we can say that Bn is a subgroup, normal subgroup, in fact, because we are in F2 over here.
So everything is commuted.
Yeah, exactly. Yeah. So Bn is a normal subgroup of Zn. Zn is normal subgroup of An. And yeah, so I can give an example. So if we draw a torus here, just imagine that the left side and right side are actually connected, you know, and then an N cycle could be something that looks like this. So if I have this a one chain that looks like this, you can see that it is an N cycle because the boundary of the cycle would be, you know, this thing, this thing, this thing, this thing. But because they all overlap together, the boundary of the first red one would be this thing and this thing. Why does it cancel? Yeah. And then the second one would be the one on the left. And because it's F2, this would cancel out. So this blue one will no longer be there. And then we still have this one. And lastly, the third one, red chain's boundary, the third red edge boundary will be over here. So this one will be removed. And then this one will also be removed. I don't know why it's not removing, but yeah, it'll be removed. So there's no boundary. Yeah. But an N boundary, an example of N boundary would be something that looks like the previous example that we have. It would just be like a cycle like this. Yeah, so we want to say that a boundary is a cycle, but a cycle is not necessarily a boundary. And boundaries are usually what we call like homologically trivial because they can be reduced to a point. Whereas on a torus, you know, if you wrap it around the torus itself, you can't sort of constrict the cycle. And that is a cycle that's not trivial. We'll get to that a bit shortly. Yeah. So we say that two N chains, An and A prime N, are homologically equivalent if they are equal up to an N boundary Bn. So if you have an N chain An, and then another an prime. If you can just find some sort of n boundary, Bn, and then if you add them in Zmod 2, if they give you the same thing, then they are equivalent. So an example will look something like this. If you have a grid again, and then if you have one n chain that looks like this, right? And then you add if you have, let's say, this particular if you add the boundary of this particular square, which is that looks something like this. We can say that the blue end chain and this new red end chain that I'm about to draw are the same. Because when you add the blue lines and the black lines together, it gives you the red lines. When there are two lines on the same edge, you cancel out. So we say that the red chain and the blue chains are homologically equivalent. And then the nth dimensional homology group is defined as, each n equals to, it is the quotient group of Zn and Bn, like Zn divided by Bn, which can also be defined as the following. Because Zn is defined to be cycles, they lie in the kernel of the boundary operators. So everything that has no boundary would be in Zn, cycle. And then Bn is the boundary of some non-trivial entity in the previous round. So it is in the image of the n+1 like partial boundary operator. Yeah, so this is kind of like an important definition that you guys should try to remember, because it's going to come up later again. Yeah. Any questions so far? I hope it's still, maybe you guys already know most of this, I don't know. Yeah, it's just, yeah, it's the,
So the boundary which you have drawn, and if you go back to the previous slide, I guess.
Mhm.
So the red things you said form a boundary.
the red things, yeah, they form a boundary because they are the boundary of this blue square in the middle. So so those form like homologically trivial things, because those boundaries you can sort of add for free because they are like just natural boundaries of the squares kind of thing. And then cycles contain boundaries, but they also contain like if you have something that looks like, that goes across the thing. Yeah, and then that itself, it is not the boundary of anything. It just happens to not have a boundary. That's all. Yeah. Yeah. All right. Yeah, so those are kind of important because now I will talk about why they're important. Like they have a very nice relationship with CSS codes that some of you might already know. So this, as mentioned earlier, because CSS codes, you can have two different stabilizer check matrices, one for X and one for Z. You can define them as two different stabilizer check matrices for an NK DX DZ CSS code. DX is like the distance for X errors. DZ is the distance for Z errors. N is the number of qubits, NX is the number of X stabilizer generators, NZ is the number of Z stabilizer generators. And then you can sort of obtain this very nice thing. Yeah, I think this is possibly one of the reasons why like Daniel Gottesman, he asked this question like whether polymer error correction is fundamentally like homological, because I mean this is probably sort of with respect to this thing. You can see in a moment. I'm just trying to write out the stuff. So we have a couple of different vector spaces. This one is the Z stabilizers. We are now associating that with our A2 vector space. and then it is F2 to the NZ. NZ is the number of Z stabilizer generators. And then there's a boundary operator, partial 2 that takes it to A1 to qubits, which is our HZ transpose, the transpose of our Z stabilizer matrix. But I'll focus on the right, the two things on the right because it's a bit it's a bit more like, you know, useful to understand this part over here. So basically the idea here is that when you take the boundary, you know, HX on any subset of qubits, it takes you to the X stabilizer generators that are sort of associated with those qubits. So, and then, yeah, this chain complex has a very nice sort of relationship with the CSS codes because you can, you know, you can associate everything with that. And then, the equivalence class of Z logical operators, which you can think of them as like the representatives of those logical operators. You know, if you remember, our first homology group is defined as a kernel of partial 1 and then image of partial 2. Would just be the kernel of HX and then image of HZ transpose. So the kernel of HX would be all the Z operators that we can perform on the error correcting code, that sort of commutes with the stabilizer generators. That means they are kind of like they will not give us any syndromes, things that we can Z operators that we can perform to the code without giving any syndromes. But they do not fall into they do not belong into the Z operators that can be generated from the Z stabilizer generators. So this sort of goes back to the idea of degeneracies in quantum error correction, where, you know, you want things, the Z logical operators have to not give syndromes, but at the same time, they must not be trivial. They must not just be boundaries. They have to be cycles. So when you have a torus, you know, your logical operators have to go around the entire torus, because that's the only way it's not, you cannot sort of mod it out with things that you cannot mod it out with boundaries. They have to be cycles instead of just boundaries. Yeah. Happy to elaborate a bit more on this if there's any questions. Yeah. And then, all right, here comes the important part, because tensor product of chain complexes gives us our hypergraph product codes, also give us a higher dimensional hypergraph product codes. So this is like something that we need to understand reasonably well. So given two chain complexes, so like two sequences of vector spaces, we can take the tensor product of those two chain complexes, and then the L chains, or like, you know, J chains or N chains, whatever you want to call it, are given by this. So just previously we had this like A, J's and stuff, right? So this is A tensor B's L chains are given by the direct sum where I plus J equals to L of AI tensor BJ. So it's just a bunch of different you know, the direct sum of a few different vector spaces that are individually sort of tensor producted together. And then the boundary operator also becomes a bit more slightly more complex. You have, you know, something that looks like this. You don't have to be too concerned about the remembering all of these things. I will, like, you know, circle back, you know, whenever we get to those things. But this is just to give you a flavor of, like, you know, how it looks like when you take the boundary of a vector space in the tensor product complex. So you sort of take the boundary of, you know, one of the individual constituents tensor with the original constituent, and then you keep the other original constituent, you take the boundary of the other constituent, and then you sort of add them together. But because it's F2, this -1i doesn't really actually matter. Yeah. So yeah, this is how a tensor a new chain complex that emerged from a tensor product of chain complexes will look like. And then yeah, we're approaching the end of the preliminary, so just bear with me a bit more. This is the Kunev formula, because after you have a tensor product complex, you want to understand what is the homology group. And as we mentioned previously, the homology group is important because it directly gives you the logical operators. And then the dimension of the homology group also tells you the number of logical qubits that come out from a new code that you obtain from taking the tensor product of their complexes. So the J homology group of this is a tensor product complex is isomorphic to the direct sum of the ith homology group of A tensor with a J minus 1 homology group of B, and then you sum over all the different i's. But I guess the most important property here, right, it's this thing, the rank of the J homology group, because it gives you the number of logical qubits. It will be sum over all the i's. The rank of the I homology group of A times the J minus I homology group of B. And then you
I don't understand it that well, but I have a feeling that on the first line, it has to be J minus I, not J minus 1. Is that correct?
oh yeah, it's J minus I. Again, I think I missed out on that. Yeah, no, but it's correct. Yeah.
Could you define the homology group again? What it?
Oh yeah, sure. It's
Okay, I see.
it's all the non-trivial like cycles in that sense. So it's for the torus again, it's the chain around the thing, it's a cycle. So it's kind of like in the torus, you have one chain around here, and then another chain within the donut itself, through the donut. And then those chains itself, there are two, so that gives you you have two things, but for each of those different individual cycles, you can, sort of you have like two cosets, and then one of the cosets you can add a bunch of like boundaries so that they become more like, interesting looking than just one line around the thing. And then you can sort of contort the thing. So it's like sort of, if you have a line, and then you can move the line to go down, and then before it goes back up again. And then yeah. So the homology group just gives you like the group of logical representatives, the representatives of those logical operators. Yeah. And then so this gives you a formula to sort of obtain what is the number of logical qubits, because the number of logical qubits is associated to the number of logical operators in that sense. And then the rank will give you that. So this is like an important expression to understand like what is the number of logical qubits for homological product code. And then yeah, and now we are ready to talk about these things, quantum weight reduction techniques. So start off with some notation. Wx and Wz will be the maximum Hamming weight of any row in HX. Then Qx, Qz will be the maximum Hamming weight of any column in HX, Hz. And then the weight itself of the weight of the row itself, you can think of the number of qubits that each check at most acts on. So it's like the max weight of all the rows, out of all the rows. And then Qx or Qz will be the maximum number of generators of either the X or Z type that act on any qubit. Does that make sense? So an example would be, let's say if you have a matrix that looks like this, and then maybe Z, and then Z. So in this case, Wx is clearly 5, right? Because X is 5, and then Wz is clearly 3. Qx is 2 because this qubit itself is acted upon by 2 generators. Qz is also equals to 2 because this qubit and this qubit that corresponds to these columns are acted upon by 2 generators. So this is the notation that we are going to be using. And then let me just erase this thing. I will briefly talk about what all the techniques will do, but without going into detail, so that you guys, whoever might be interested in using the techniques, at least you guys have an idea of like what those techniques can achieve. So there's a technique called copying. It brings like Qx prime, like I'm getting prime for like the resulting code parameters. Qx prime will now be kept at most 3. and then WZ prime will now be QX dot WZ. So this is, you can see that this technique itself is not sufficient on its own, because sure, you remove like QX, you make QX pretty small, but WZ you know, increases, so it's not fantastic. Gauging is another technique. It brings WX down to 3. WZ prime now becomes WZ times QX times WX plus 1. And then the distance also suffers because it's now dx. Yeah, and then the technique that we are going to be talking about today is called thickening and choosing heights. This technique slightly increases WX.
In those first two techniques, WZ becomes greater,
Yes,
so it's not really a reduction.
yes, but when you use all 4 techniques, the 4th technique is called coning, you end up with a weight reduced thing. Like each of those independent techniques itself is not a, but they are all interesting on its own, because perhaps in some situation, due to whatever reasons, you want to sort of shift the weights from certain parts of the code to another parts. Yeah, yeah. Coning gives you WZ prime to most QX plus 2. Yeah. So we'll be focusing on thickening and choosing heights today. And then
dx dash is, what is that? L?
L is a parameter of our choice. I will also talk about it in a bit. And then this thickening and choosing height also reduces I think QZ to something that depends on L2. And then I'll talk about that later too. But yeah, this is just a bunch of techniques that he came up with, and then they're all like pretty
Hey,
interesting.
Samuel, I have a question about the techniques.
Oh, sure,
So-
yeah.
So all these 4 techniques, do they change the code length and the code dimension?
It doesn't change the number of logical qubits. I didn't catch your first parameter that you were talking.
So code length and the number of logical qubits do not change.
Number of logical qubits doesn't change, code length changes.
Code length changes.
Yeah,
Okay, okay,
yeah,
thank you.
yeah, good question. Yeah, it's like the cost that I think Sasha was mentioning earlier too. It's a cost that you have to decide whether it's worth it for your, you know, architecture or like yeah. Okay, now we'll be diving a bit more into detail for thickening and choosing heights. So as mentioned before, if you have a NKD CSS code queue, you know, it's sort of associated to a 2 complex. You know, just this will be like A2, A1, and A0. Just a quick recap. A2 is our Z stabilizer generators, A1 is our qubits, A0 is our X stabilizer generators. And then let's say you have a L1L classical code C. There's a 1 complex B. So you know, yeah, I'm not sure whether it's like you know, it's, yeah, so classical codes also have like a homological picture to it, which might be obvious for some of you, I don't know, but it's you know, you can think of the B1 itself as checks here. These are the checks, and then these are the bits, right? Because if you take the opposite direction, it'll be HR without the transpose. When you apply HR on the bits vector space, you get the checks vector space. So you get a syndrome that scales with the dimension of the checks, if that makes sense. Yeah. And then L is the length of the repetition code. L1L is the repetition code. HR is the check matrix of C. And then now we have a new code that we call the thickened code Q prime. That corresponds to now a 3 complex, because you know, just now we talked about when you take the tensor product of a 2 complex and a 1 complex, you end up with a 3 complex. And then this T, you can write down the different vector spaces. So you have a 3-dimensional objects. So you can think of them as cubes in the geometric picture. There's this dimension. And then the 2-dimensional objects, the plaquettes, now become a lot bigger. This is why when Sasha brought up the overhead, right? We say that now we have more stabilizers, and we also see we have more qubits than before, because we have now NL plus NX, L minus 1. Then T0 is our X stabilizers. Now also increases. So I want to say that this thing itself is sort of redundant, because as mentioned before, a CSS code only needs, like a sub 2 complex to be sort of well defined in that sense. And then this is Z, this is qubits, this is X stabilizer generators. But those redundancies are actually pretty useful for those who are interested in, like, single shot decoding and stuff, because these are what we call meta checks, because they kind of check how accurate your Z stabilizer generators are. But we're gonna ignore that discussion. But just for those who are interested, those higher dimensional objects that are on the other side of the Z checks and the X checks can actually give you some information on how well you're doing decoding. But this quantities, right, basically like the the direct sum expressions that I was writing in the previous slides on the tensor product chain complexes. This is how you obtain the dimension of the vector space. Any questions at this point?
So the T3, the meta checks are checks on the syndrome itself.
Yeah. So if you get some syndrome that doesn't make sense, your meta checks can give you information. But in this case, we are sort of disregarding that. But it's just something, if you choose to keep the redundancy, you want to keep the overhead, then you can actually sort of use those things to your advantage if you feel like you need them. Yeah. But otherwise, this part is like sort of, we don't really care about them. And then we are working with the CSS code that's sort of over here. Yeah. Any other questions? No. I will give you like a very nice picture that was sort of painstakingly constructed using TIC-Z. But anyways, this is an example of like a regular surface code. For those who are not familiar with the surface code, the edges itself are the qubits. The gray balls are the X stabilizer generators. The red plaquettes are the Z stabilizer generators. And then as mentioned before, like the chain complex kind of structure, you see that the Z stabilizer has the qubits as its boundary, because those black lines are bordering it. And then the qubits have the X stabilizers generators as their boundary, because the black balls are around them. And then in this particular case, in picture A, right, we have a surface code with dx equals to 2 and dz equals to 3. It's a bit different from the usual surface code where it's like squarish. In this case, we have a irregular distance because it's easier to make on TIC-Z. But so the idea here is that for those who are not familiar with the surface code, dx is 2 because you just need 2x errors. Let's say you have 1x errors here and 1x error here. This is a logical operator because it commutes with the Z stabilizer generator. That means it doesn't throw off any syndrome. And at the same time, you can't generate this X logical error from the gray balls. Like the boundaries of the co-boundaries of the gray balls can't, individual gray balls can't generate those things. And then dz is equals to 3 because you need something that looks like let me just erase the previous one. dz is equals to 3 because if you have a z error here, z error here, z error here, the these balls, right, they can't detect those errors because they have even parity on both sides of them. Yeah. So this is the original surface code, but now we thicken it with an L equals to 3 repetition code. So you can think of a repetition code at the side over here. If you remember our repetition code, we define it as the 0-dimensional objects are the bits, and then the 1-dimensional object are the checks. So this is a repetition code. So you can think of it, this is the reason why Hastings called it thicken, because you add another dimension, you sort of like live up the entire thing. So now it becomes like if you have something that was 2-dimensional, now you have something that's 3-dimensional. And then all the red squares are still your Z stabilizers. So now you can think of them as having copies of the same codes at the different heights. And then between each layers, you have new quantum bits as well as checks to connect them. So the yellow ones, I don't know how to create yellow on this color, but I'm just gonna write Y here. It's gonna be our new Z stabilizer generators. So they check the qubits between each layer. And then you also have some additional quantum bits, the black lines here, that sort of like, bridge between the layers together. And then in this case, after thickening, we now have dx prime equals to 6 and dz prime equals to 3. So dz prime is obviously still the same because if you do something like this, you still have the same X stabilizer generators that combine the things, so you can't be shorter. But your X becomes a bit more interesting because if you look at your X errors now, right? Initially we say that this and this on the other side is a logical operator, but now because of the additional yellow Z checks, right? This X errors no longer commute with all the Z stabilizer generators. So instead, it has to crawl all the way up. If you think about it, it has to crawl all the way up because of the repetition code structure. It now has to crawl all the way up, so that it commutes with everything, and then and still not generable. It cannot be generated by the X stabilizer generators. Yeah.
So this is only generating new Z stabilizers across the vertical direction, right? It's
Yeah.
not generating any new X stabilizers.
No new X. Well, the X stabilizer generators become a bit more interesting too. If you see, like in each of those individual layers, they now have to connect. They also have to act on the new qubits that are formed. So like the degree increases by like 2 in this case because of the repetition code structure, because you have to connect between the layers. Yeah. Yeah, the distance increases. This is why like yeah. Any other questions about this thing? Hopefully this diagram is helpful. Yeah.
So in this particular example, the code length in B is 3 times larger than code length in A. Is that right?
It's a bit more than that. If you look at this expression that I gave here, so n of let me change it to a laser pointer. The n here, right, is the original code length. Is now n times L plus nx times L minus.
Oh,
Yeah.
I see.
Yeah.
Okay.
Yeah. Yeah. But this is a pretty useful trick to boost the distance of your code in a particular direction. And then you could also apply thickening in a different basis, and then both your X and Z would increase, but obviously at some amount of overhead that you have to incur. And here comes the more interesting part that I think is pretty cool, choosing heights. So because of the repetition code structure, you can actually chuck away some of the Z stabilizer generators. So initially we have like 9 rate things, right? Like we have 9 rate things, but you can, for each of those things, you can choose a particular height that you want to pack it at. So you don't have to keep all 9 of them. So for this vertical column, right, that corresponds to an original 1Z stabilizer check, you can choose one at some height to keep it. And then for this one, you can keep a different height, and then you can choose another one to keep at a different height. And then this is sufficient because of it's like an overcomplete set of checks, if you get what I mean. So one way to see this is that if you keep the yellow checks, this original, it's a bit hard to show this part, but this original flat check over here, right, in the second floor of this building, can be generated from a combination of this vertical yellow check, the one at the back here, as well as the original Z check. If you apply all of them, you get the one at the top here. Does that make sense? Basically, if you apply Z's on this qubits, and then the one at the back, this qubits, and then the one at the bottom here too, you end up with this layer at the top here that we removed. So it means that you only have to keep one for each floor. So this is the reason why QZ decreases after you choose heights. QZ prime is lesser than original QZ, because if you choose the heights correctly, let's say you have an original qubit over here. It was acted upon by, you know, two or potentially more that's not drawn in this. If it's some arbitrary code, you could be applied on many different things. But if for each of the Z checks around it, if some of them were packed at a higher height, now you no longer have a QZ equals to 6. It could have been QZ equals to 2, 3, depending on how sparse you make the thing. Yeah. Is that clear how like choosing heights reduce the thing? So yeah. Okay, nice. And then last preliminary part, just check the time. So choosing heights is a pretty cool thing. If you guys from E, so you probably know balls and bins better than me. But it's actually like a balls and bins problem. You know, you can think of you're having like L different bins, and then you choose like you know, balls to drop into different bins. So there's this lemma that Hastings came up with. So W can be defined as sort of like the, you know, max number of Z step that you want to act on any qubit. And then so you can think of like you have W balls, and then for those L beans, right? This is just an upper bound on the probability of us having more than W balls in a bean. You can sort of, this is just an approximation that's pretty nice. And then, you know, you just use the Lovász local lemma to show that this is like the amount of like dependence on the different events. And then you can show that as long as you choose L sufficiently large that this equation holds, there is non-trivial probability, or there is a choice of heights. That means you can pack different things in such a way that the QZ prime, which is the QZ of your resulting code after thickening and choosing heights, now has a maximum W plus 2. W comes from this quantity, number of Z stabilizers that you want to act on any qubit. The 2 comes from the repetition code because there's one at the top and one at the bottom. So you necessarily have to add 2 to it. And then and WX. So this is just a pretty cool thing that I thought was pretty interesting to talk about. All right, now we are ready to talk about the main results. So yeah, I'm sorry, it's probably took a bit longer than I wanted to. Yeah, but anyways, hopefully those discussion was useful. Maybe it gives you a different interpretation of classical error correction too, because you can also think of things in terms of a chain complex, but the notion of homology is probably less useful because of the lack of degeneracy. Maybe there is degeneracy, I'm not too familiar with that. But anyways, since Hastings came up with the paper, people have generalized thickening. So there's this new technique called distance balancing. So the key difference, I'm just gonna focus on the key difference. So instead of choosing a repetition code, you can choose an NC-KC-DC, a classical code that also has a one-dimensional complex, you know, associated with it. And then as long as the check matrix of that one classical code is has no like, you know, redundant rows, the resulting quantum code that's constructed from the tensor product in the complex now has a very, instead of retaining the number of logical qubits, you now have a K times KC. And then dx prime now becomes dx times dc. And then dz prime equals to dz. I think this is pretty cool, because if you choose a good classical LDPC code, which means that, you know, the number of logical bits scales linearly with the number of bits, and then the distance scales linearly with that, you get some pretty nice, you know, asymptotically, if you have a pretty small quantum code and then you sort of distance balance it with a very large classical code, you can sort of make the quantum code's parameters look pretty good, at least in one particular basis. Does that comment make sense? The idea is that if you choose a classical LDPC code, a good classical LDPC code, and you tensor product it with you know, like a maybe so-so kind of like quantum code, you can actually make its distance pretty nice in one dimension. And then you can make the logical qubits pretty nice too. But
what's the relation between N prime and NC?
N prime and
So you have a relation between K prime and KC, DX prime and
Oh,
DC.
oh, yeah. That's a great question. It actually goes back to this previous Massey expression. So this thing itself
Oh,
is
okay,
M
okay,
prime.
still here. Okay, understand. Okay.
Yeah. Yeah, so it's yeah. So, but anyways, I just think this is a pretty cool technique. And then it gives you some pretty nice parameters. And you can distance balance it in one basis. So you can boost the X distance first, and then you can distance balance it in Z distance, and then you boost the other distance. But obviously the rate of the code will suffer pretty bad, because you can think of, as the dimension increases, your the stuff that you get is just gonna be not as good.
You mentioned, along the way, you mentioned LDPC classical code, but this is the first time, not the first, but this low density did not play any role in the discussion of the construction. This is, you take this classical code to be LDPC because do you want the resulting code to be LDPC, or what is the reason?
Yeah, that's one reason. So if you choose a LDPC code over here, a repetition code is also LDPC. So that was kind of essential. I guess I didn't mention the part. If you choose a LDPC code here, like by the tensor product structure itself, the resulting code will also be LDPC. And if the sorry.
Repetition.
In the original introduction on the thickening and choosing heights, the thickening itself, we use a classical repetition code. So that the resulting checks that come up from the tensor product between a repetition code and a quantum code will also be LDPC because of that. And then in this case, if you choose LDPC, a good LDPC, classical LDPC code, the tensor product it with just our CSS quantum code. Again, we also have another LDPC quantum code, but this time around, the distance property will scale like this, but because DC itself scales linearly with this is like O of NC, right? Right, if it's a good classical LDPC code, and then the resulting N prime of this new quantum code, if like we choose a large enough classical LDPC code, it can sort of make the overall quantum code go closer asymptotically to having good distance in the X basis. Yeah. So this is the main result. One that I want to share. So basically, if you have a quantum code with distances dx and dz. Oh, there's someone's calling. Sure. How does it work?
Reshare the screen. Oh, it's shared.
No, you're sharing.
Got it. Yeah.
Okay, perfect. Yeah. Sorry, minor hiccup.
Just drag it to the side.
Oh. Like this? Okay, nice.
Yeah, that's one.
Yeah. So the idea is that if you have, let's say your original quantum code has effective distances dx and dz bar, with m. And m is some single ancilla stabilizer measurement schedule. Recall that we say that the effective distance is defined with respect to some measurement schedule or circuit. And then if you have a distance balanced quantum code that is a result of Q and some classical code C, then the resulting distance balanced quantum code, we can construct a new single ancilla syndrome measurement schedule such that this is the resulting effective distance.
So when you're saying schedule, you mean the circuit basically, the measurement. When do you do the measurement, the order of the measurement?
Yeah, so I kind of like loosely interchange between schedule and circuit, but schedule is maybe a bit more broader because the order of the generator measurement actually kind of matters too, because sometimes the order can cause the errors to propagate in a more like terrible way. And then, but the circuit itself, is there?
Ordering of the measurement.
So
Yes.
the time order.
Well, that's in the first single and still figure in the beginning.
Yeah.
Yeah. Yeah, so I'm just saying that, whatever your effective distance was with respect to a single ancilla stabilizer measurement schedule, you can preserve the gains in the distance that come from distance balancing, with some other single ancilla measurement schedule too. That's closely related. Yeah. But this result can be more general for hypergraph product codes that I'll talk about later. But
Still struggling a little bit with this distance balancing because you are multiplying in one direction, so one distance becomes much larger than the other, and somehow this is nevertheless called balancing. One distance is much larger, the x is much larger,
mhm,
this is very small,
mhm.
and they're called balanced.
Oh, I guess if it was imbalanced in the first place, then you know it becomes
So if
balanced.
they were, to start with, they were unbalanced, right?
Yeah, but you could, I guess it's like you know, maybe some notion of, I don't see as there's like load balancing too. You try to move. It's,
Yeah, it's boosting, I would say.
yeah, could be a confusing name, I
Who
guess.
came up with that name?
I think it's Evra, Kaufman, and Zimor.
Zimor?
Yeah, it's in their paper like that.
All right.
Um, okay. So I'm gonna briefly give you a high level intuition of how the proof sort of goes about. And then before we go into the weeds of the details. So the idea is that a distance balance code actually has a very nice geometric layout with rows and columns. And then the idea is to show that we show that each new generator that emerges from distance balancing, they only act on, you know, either some individual row or some individual column. And then so if you have any hook errors that come out from those generator measurements, they only impact a row or a column of qubits. And then next thing, we want to show that using a canonical logical operator basis of the distance balance code, we can lower bound the number of rows and columns that have to be inflicted with errors in order for like the errors to actually be a logical error. Does that make sense? So the idea is that I'll just repeat one more time again, just to make sure it's clear. There's a geometric layout where you have rows and columns of qubits. And then we want to show that each generator that you measure only impacts either a row or a column of qubits. And then, so that's like bounding how much error can propagate. So if you have an error in the ancilla qubits, it only propagates to one row or one column. And then we then show that a logical error of the distance balance code has to span at least like, you know, some number of rows and some number of columns. And therefore, there's this robustness that we talk about. Yeah. So this is the geometric layout over here. Notice the rows and columns. There's a NC minus KC. Those are the classical code parameters. And then NZ, N, and NX are the quantum code ones. So over here, you can think of one long column over here is one copy of the quantum code because the X stabilizers will act on the qubits like this. Z stabilizer will act on the qubits like this. And then in addition, because of the classical code itself, we not only have NC copies of the quantum code, but we also have, you know, this things that act sideways. So this new Z stabilizers, they act on these qubits in the form of, in the same way as the classical code will act, because this is what's happening down here. The classical codes are the horizontal direction, and then the X stabilizers act on the qubits over here in the transpose direction of the check matrix of the classical code. This might be a confusing part, so feel free to stop me and ask me if you have questions. So I can reiterate briefly. Copies of quantum codes, original quantum codes in the columns here. And then you can think of copies of classical code in this direction. Oh, sorry, not this direction. This directions. Because these are the bits and these are the checks. And then the bits here correspond to NC, the checks here correspond to NC minus KC. So these are copies of classical code. And then in this direction, it's the kind of like the opposite direction where the bits are the classical check and then the stabilizers are the original bits. So the direction is like the transpose of the check matrix. Yeah. Is that clear? So as you can see, already that there is a lot of structure in the tensor product structure, which is kind of important why we sort of have this notion of row weights and column weights. So if you have some operator that acts on some subset of qubits, let's say acts on this qubit, 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 and this qubit. And then all of these are X. So we have let's say we have some like X operator that acts on this qubits. And then we define XAR to be the A qubits with the X errors inflicted, but the number of rows in this A region that are inflicted with an error. So in this case, we have 1 row, 2 row, 3 row, and 4 rows. So XAR is 4. And then XAC will be the number of columns that are inflicted with errors in the A area. And then we have 1 column, 2 column, 3 column, and 4 column as well. So this is 4. So this is just to sort of formalize sort of like the impact of an operator on the qubits in these different regions in our geometric layout. And then to sort of introduce the notion of like row weights and column weights of errors. Is that clear? Any questions on this part? Yeah. And then this lemma is really long, but all I'm just trying to say is that a Z stabilizer in the original code can only, let's say you use a single ancilla measurement schedule, and error happens on the ancillas. So this particular Z stabilizer generators only act on qubits in this column. So the column weight of the error is just at most 1 column. An X error here, let's say there's an error in its ancilla qubit. So even if you use a single ancilla on it, if you have an error, it acts on at most 1 column, but perhaps a row, the number of rows that it affects scales according to the weight of the X stabilizer generator. And then obviously there's also like the columns over here and then the rows over here with the same kind of like argument. So this is why this geometric layout is super helpful, because it helps you to bound. Let's say if you have 1 error in your ancilla, in your single ancilla measurement circuit, at most it either influences 1 column or 1 row. And then the next step is to sort of show that any logical error will need at least D rows or D columns or something along those lines. And because of we upper bounded the propagation of the error and we lower bounded how big the error has to be, we can sort of say like, oh, we need, even after considering all the ancillary errors, we need this number of errors for the logical error to happen. Is that clear? Like I think it's a pretty there's a pretty good geometric like intuition for why this should work, even if the math seems like pretty, complicated to sort of follow later. It's getting kind of late, so I'm going to speed up a bit and not go into some of the details of the stuff. But I just want to talk about the canonical logical basis. So the X logical operators of the distance balance code actually has a very nice structure. So on the left side is region A, right side is region B. And then I'm just going to write out very quickly so that I can briefly comment on why this makes intuitive sense. RS is just like the row space. Idea is that you can construct a complete basis for the X logical operators just from looking at region A, this region itself, and then this side over here is pretty intuitive because this is the X logical operator of the original quantum code. And then kernel of HC is just the classical code's logical operators. So you can think of this as like the rows for each column itself, the rows have to sort of look like a logical operator in the first place. And then you have to duplicate it across the columns such that it matches, the column indexes have to match the classical code word of the classical code. Yeah. And then similarly, Z logical operator, okay, maybe it's not so similarly, but the Z logical operators will have to look like the X logical operator of the original quantum, sorry, the Z logical operator of the original quantum code. But then it has to sort of like this one is a bit harder to explain, but it's yeah, it's just like lies in the complementary space of the row space of the classical parity check matrix. So there is some pretty nice geometric intuition. Any questions on this? I'm not going to prove this. Initially, I was trying to do, but I think we don't have that much time, and then it's probably not so essential. So a geometric picture will look something like this. So, let's say there is a classical code word. Let me just remove this. For Z logical operator, for X logical operator, it can look something like this. Let's say let's pick a classical code word that has support on this, and this, because we mentioned that this direction, right, is the classical code words parity check matrix. So let's say these three blue circles are the classical code words. And then let's say an X logical operator in the original quantum code has this thing. And then this, if you apply X on this 9 qubits, you have an X logical operator of the distance balance code. Yeah. And then now we come to the more like a challenging part, where it's like, how do we bound the number of rows and the row and column weights of the logical errors? So this lemma is probably the most essential one.
So, I hate to interrupt you, but it's been about an hour and a half.
Yeah.
Kind of synchro.
Yeah, I'll just
Write this up in 10 minutes.
yeah, sure. That's good. So I guess, it's just the main proof technique behind the thing is to sort of show that any linear combinations of X logical operators as well as X stabilizer generators, it will still span like the number of rows or columns in that sense. And then for the Z logical operators, it's a bit more complicated because there are stabilizers on both sides that can annihilate our operators, so it's harder to analyze. But we use a proof technique that's similar to what Tillich and Zimor use for the hypergraph product codes. So sort of like by looking at restrictions on the parity check matrices, we can argue that if you restrict it to something that's too small, that doesn't span the distance that's required, there is no more logical qubit, and therefore like it cannot be a logical operator. Yeah, that's the intuition. And then you combine those lemmas, the upper bound and lower bound that I was talking about, then you can show that the distance is that. And then I will not talk too much about hypergraph product codes, but I will just say that distance balancing, the idea of tensor products is inherent in the hypergraph product structure, because you see you have this like one classical code here and another classical code here. You take the tensor products of their complexes, you also get hypergraph product code. So there's a high level intuition. And then the higher dimensional, okay, I have mentioned this previously already, but basically it's recent result from last year that for if the D is distance of a hypergraph product code, the effective distance using any stabilizer measurement circuit is also D. And then
What was the authors of this work?
sorry,
Who are the authors?
Main and Clays, Jahan Clays and Akiris Main. Yeah. And then this is the main result too. It's kind of long, but the idea is that because I have to define what a higher dimensional hypergraph product code is too. But the idea is that the idea is that instead of just tensor producting it once, you tensor product it many times. So you have a complex that's very high dimensional. And then the main result one, you can think of it as the inductive step that we can use and prove by induction to show why this is true. So and then the base case would just be this previous result, because the base case is basic hypergraph product code. You tensor product it multiple times, and then each time you use our argument from earlier. So that will be the inductive step, and then that's how you show a higher dimensional hypergraph product code can have its original code theoretic distance as its effective distance for any stabilizer measurements. Yeah, that's the high level intuition. Sorry, I didn't get the timing really right, but you guys had a lot of really good questions. it's a yeah, but that's about it. I guess.
Large amount of stuff. It's difficult to discuss this within one sitting.
Yeah, and then I guess for like future work, you know, didn't really consider the optimality of like the single ancillar schedules that we talked about, whether better schedules exist. We didn't consider effective distance preservation of coning, which is a really cool technique from Hastings that you guys should check out if you guys are interested. And then we can also talk about weight reduction while preserving other interesting code properties, like maybe some like transversal logical gates, because all those things were not prioritized when Hastings was sort of coming up with those techniques. So those properties could be interesting too. It's a bunch of references, and then yeah, thank you guys for the attention.
Go back one page to see the references.
Oh. So
That's it, stop.
oh sure, yeah. Yeah, this is the one that you asked me.
Yeah. Nine's class.
Yeah. Yeah, I think he's at Google now. He's at U Chicago now. Yeah. You guys are interested in talking to them for any reasons.
Thank you. Thank
Yeah,
you very much.
Yeah. 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 You guys have any questions? I know it's really long, and I mean, homology is probably not widely used in classical